Winter in a Montana territory didn't forgive mistakes. A poorly designed heating system meant frozen water buckets by morning, frostbitten fingers by noon, and sometimes worse. Yet in the winter of 1879, while his neighbors fed their fires every 2 hours through the night, one man's cabin stayed warm long after his flames had died. They called him reckless. They called his design dangerous. Some called it impossible. But when the coldest night in 20 years arrived, his hidden fire pit would prove that ancient wisdom often outperforms modern certainty. If you're interested in forgotten frontier engineering that actually worked, hit that like button, subscribe for more historical survival wisdom, and drop a comment telling us. Have you ever seen underfloor heating in an old cabin? Bitterroot Valley, Montana Territory. November 1879. The first heavy snows had already arrived, and Mikko Jarvinen was doing something his neighbors considered insane. While other settlers were chinked and ready for winter, the Finnish immigrant was tearing up the floorboards of his nearly completed cabin to dig a pit beneath them. A large pit, 3 feet deep for feet wide, lined with river stones he'd been hauling for weeks. "You'll burn the whole structure down," warned Thomas Bradley, an experienced builder who'd constructed 7 cabins in the valley. Bradley had stopped by with 2 other settlers, ostensibly to help, but really to talk sense into the Finn. Fire belongs in a hearth, against a wall, with a proper chimney, not under your feet. Mikko didn't argue much. His English was limited, his explanations even more so. He simply continued fitting stones into the earthen chamber, selecting each piece with care, rejecting limestone, choosing only dense sandstone and river granite. The rocks had to be specific, dense, capable of holding heat for hours. "It's a waste of good stone," muttered Samuel Peters, who ran the closest trading post. "And a waste of labor. That pit will draw cold air up through your floor all winter. Mark my words." But Mikko understood something these men didn't. In the forests of Finnish Karelia, his grandfather had built a taka, a masonry heat chamber that stored warmth in stone and released it slowly through the long Arctic nights. The principle was simple: thermal mass. Stone, when heated sufficiently, becomes a battery of warmth. Not the quick, consuming heat of an open fire, but patient, radiant warmth that could outlast the flames by many hours. He laid the final stone on November 28th. The pit measured 42 inches across and 36 inches deep. Above it, he installed a removable iron grate, then replaced the floorboards with careful gaps for heat to rise. The whole system sat 8 inches below the cabin's main floor level, invisible except for the loading door he'd cut into the side foundation. What did this Finnish immigrant understand about heat storage that experienced American builders had missed? Stay with us, and if you're learning something new, show your support with a like. The engineering was deceptively simple, which made the mockery worse. To his neighbors, Mikko had simply buried a fire pit and covered it with wood. To him, he'd built a radiant heat engine. The key lay in the stone selection and arrangement. Sandstone and granite possess high specific heat capacity, the ability to absorb and retain thermal energy. Limestone, which his neighbors used freely in their chimneys, was lighter and fractured under repeated heating cycles. Mikko had rejected every piece of limestone. He'd arranged the stones in layers. The bottom layer, 8 inches of small river rocks for airflow and ash collection. Middle layer, large, flat sandstone slabs that would absorb maximum heat. Top layer, rounded granite stones positioned 2 inches below the iron grate. These would radiate heat upward most efficiently. The physics were precise. When wood burned in that chamber, temperatures would reach 800 to 1,000 degrees Fahrenheit. At those temperatures, the surrounding stone mass, approximately 2,400 pounds of it, would absorb tremendous thermal energy. Sandstone's specific heat capacity is roughly 0.2 BTU per pound per degree Fahrenheit. That meant his stone battery could theoretically store over 100,000 BTUs during a single 3-hour burn. "You're going to suffocate in your sleep," declared Bradley when he saw the finished installation. "Carbon monoxide will seep up through those floor gaps. I've seen men die from less foolish arrangements." Others agreed. The county's sole physician, Dr. Whitmore, stopped by in early December to add medical authority to the chorus of concern. Subfloor combustion chambers are documented fire hazards, Mr. Jarvinen. The Denver fire of '74 started exactly this way. Miko tried to explain the ventilation design, how the pit drew air from outside through a dedicated channel, how the chimney draft was actually stronger because of the underground positioning, how the floor gaps were precisely sized to allow radiant heat but not smoke. His English failed him. Their skepticism didn't. By mid-December, the story had spread. The Finnish homesteader with the suicide heating system. Some neighbors stopped visiting entirely, certain they'd soon be attending a funeral, probably helping to extinguish what remained of his cabin. They were so certain he was wrong. But thermodynamics don't care about consensus. Keep watching to see what happened when winter truly arrived. And don't forget to subscribe for more forgotten engineering wisdom. January 11th, 1880. The temperature at sunset was already 12 degrees below zero. By midnight, it had dropped to -22 Fahrenheit. By 3 a.m., when Thomas Bradley woke to add wood to his fire for the fourth time that night, his outdoor thermometer read -28, the coldest temperature recorded in the valley in 20 years. Bradley's cabin, considered well-built by territorial standards, required stoking every 2 to 3 hours. He'd burned through 18 logs since sunset. His wife and 2 children slept in their coats, huddled under elk hides near the hearth. The cabin's far corners, 15 feet from the fire, hovered around 38 degrees. The water bucket had frozen solid despite being only 8 feet from the flames. 3 cabins over, Samuel Peters was having worse luck. His fireplace, built with the limestone everyone said was perfectly adequate, had developed a crack from thermal stress. Cold air poured through it. He'd stuffed it with clay and rags, but his children's breath still formed clouds indoors. He'd burned 22 logs and was running low on split wood. At Miko Jarvinen's cabin, something different was happening. He'd loaded his underground chamber at 6 p.m., a careful arrangement of seasoned pine and oak stacked to allow maximum airflow. The fire burned hot and fast as designed. Flames consumed the wood in roughly 2.5 hours. By 8:30 p.m., only glowing coals remained. By 9:15 p.m., even those had turned to ash. The fire was completely dead, yet the cabin remained warm. At midnight, when Bradley was making his second trip to the woodpile, Miko's cabin measured 62 degrees Fahrenheit near the walls and 68 degrees directly above the stone chamber. His children slept in their regular bedclothes. His water bucket showed no ice. At 3 a.m., when the outside temperature hit its brutal low, Miko's cabin had dropped only to 59 degrees. The stone beneath his floor was still radiating heat, patient, even comfortable warmth rising through the carefully spaced floorboards. Bradley noticed Miko's cold chimney during his 3 a.m. wood trip. No smoke, no glow from the chimney top. He almost wanted to check if something was wrong, if the family needed help. But the thermometer demanded his attention. His own fire was dying again, and his fingers were already going numb. At dawn, when the valley began to stir and the temperature had warmed to -18, Bradley walked over. He had to know. He knocked, expecting to find the family huddled and miserable, too proud to admit the heating system had failed. Miko opened the door in his shirt sleeves. Behind him, visible in the early light, his children were eating breakfast at a table, not huddled by a fire. The cabin was warm, genuinely, comfortably warm, and had been all night. How much would? Bradley asked, his breath fogging in the doorway. Miko held up 3 fingers. 3 loads, 1 burn, approximately 14 logs total. Bradley had burned 31 logs through the same night, and his cabin had never been truly warm. The numbers were undeniable. But how exactly did those stones hold enough heat to last 14 hours? The answer reveals engineering principles that modern heating systems are only now rediscovering. Hit that like button if you want to see more historical innovations that actually worked. What happened in that stone chamber beneath Miko's floor wasn't magic. It was thermodynamics working exactly as designed. When wood burns at 800 to 1,000 degrees Fahrenheit, It releases between 6,000 and 8,500 BTUs per pound. MECO's 3-hour burn, consuming roughly 42 pounds of wood, generated approximately 280,000 BTUs of thermal energy. In a conventional fireplace, most of that energy escapes up the chimney. Studies from the period suggest that open hearths captured only 20 to 30% of available heat. The rest vanished into the night air, which is why frontier families needed constant fire tending. MECO's system worked differently. The enclosed stone chamber captured between 65 and 73% of the combustion heat. That thermal energy didn't immediately radiate into the cabin. Instead, it soaked into 2,400 pounds of carefully selected stone. The sandstone absorbed heat first, its dense crystalline structure trapping thermal energy. The granite, with slightly different thermal properties, absorbed heat at a different rate, creating a staged release system. As the fire died, the stones began their slow discharge, radiating warmth upward through the iron grate and floorboards, downward into the earth, which acted as additional insulation, and horizontally into the surrounding foundation stones. The heat release was remarkably even. During the first hour after the fire died, the floor surface measured approximately 105 degrees Fahrenheit, warm to the touch but not burning. By hour 4, it had dropped to 95 degrees. By hour 8, roughly 82 degrees. Even after 14 hours, the stones were still noticeably warm at 72 degrees, keeping the cabin comfortable while outside temperatures remained well below zero. The mathematics were elegant. Each degree of temperature stored in 2,400 pounds of stone with a specific heat capacity of 0.2 BTU/LB/degree F represented 480 BTUs of stored energy. Heated from an ambient 50 degrees to an average of 400 degrees during the burn, the stone mass stored approximately 168,000 BTUs, enough to heat a 400-square-foot cabin through the longest winter night. By late January, word had spread beyond mockery into curiosity. Thomas Bradley was the first to ask for details. Samuel Peters came next, notebook in hand, wanting measurements and specifications. By February, 4 other families were planning similar installations for the following autumn. Dr. Whitmore, who'd warned of carbon monoxide poisoning, conducted his own investigation. He found that MECO's ventilation design, drawing combustion air from outside through a dedicated channel, actually created negative pressure in the burn chamber, pulling smoke down and out through the chimney rather than up through floor gaps. It was safer than conventional fireplaces, where downdrafts could push smoke into living spaces. The fuel efficiency was impossible to ignore. Through January and February, MECO's family consumed approximately 40% of the firewood their neighbors used. One evening burn lasted through the next day's cold. When temperatures moderated above 10 degrees Fahrenheit, a single fire could keep the cabin comfortable for 24 hours. Traditional knowledge wasn't primitive. It was precisely engineered for survival. These weren't superstitions. They were solutions tested through generations of Arctic winters. By autumn of 1880, 11 cabins in the Bitterroot Valley incorporated variations of MECO's subfloor heating system. Thomas Bradley built one using MECO's exact specifications. Samuel Peters modified the design, extending the stone chamber along 2 walls to heat a larger structure. Even Dr. Whitmore, the physician who'd warned against the suicide heating system, installed a smaller version in his medical office. The adaptations varied, but the principle remained constant: thermal mass storage using stone chambers beneath or within a living space. Some builders used soapstone, which has even higher heat capacity than sandstone. Others experimented with brick, though it proved less effective than natural stone. A few attempted to use metal radiating surfaces, but found that metal, despite heating quickly, also cooled too fast. Stone's slower thermal response was actually the advantage. The system spread beyond Montana. Trappers carried the knowledge into Wyoming and Idaho. Norwegian and Swedish immigrants recognized the principle immediately. It resembled their own Pisov masonry stoves. By 1885, scattered throughout the Northern Territories, Dozens of homesteads were using underground or enclosed stone heating systems that required firing only once per day. Modern heating engineers would eventually rediscover these principles. Radiant floor heating, thermal mass storage, rocket mass heaters all operate on the same physics that Miko understood intuitively. Contemporary Siberian or Russian masonry heaters capture 70 to 90% of combustion heat using the same stone mass principles. Sustainable building designers now specify high thermal mass materials specifically for passive heat retention. The irony wasn't lost on the valley's old-timers. They dismissed Miko's design as foolish, dangerous, backward, the desperate gamble of a foreigner who didn't understand American building practices. In truth, he'd understood heat transfer better than the experienced builders who mocked him. His grandfather's knowledge, passed down through generations of Finnish winters, contained more practical thermodynamics than most engineering textbooks of the era. Thomas Bradley, in a letter written in 1889, admitted the truth plainly. "We thought we were teaching that Finn how to survive a Montana winter. Turns out he was teaching us. Pride made us slow students." The hidden fire pit heated more than cabins. It demonstrated a principle that frontier America often forgot. Indigenous and traditional knowledge isn't the opposite of engineering. It's engineering refined through centuries of trial, error, and survival. Dismissing it as primitive reveals not the ignorance of the past, but the arrogance of the present. Mikko Jarvinen lived in his cabin for 23 more years. His subfloor heating system never failed, never caused a fire, and never required more than one firing per day, even in the coldest winters. When he finally sold the property in 1903, the new owners kept the system unchanged. It was still functioning, still efficient, still warming feet, and proving that sometimes the best innovations are the ones we've forgotten. If this story changed how you think about primitive technology, show your support with a like. Subscribe for more forgotten engineering wisdom that's more relevant than ever. And drop a comment. What traditional survival technique do you think deserves to be rediscovered? The past has more to teach us than we usually admit.